So here we are with the ninth lecture in kinematics. Like I always say, please do the reading. Check out the chapters indicated in Canvas. Okay, now here we are. We're going to actually use the equations to do a lot of problems similar to your homework. Now, we are going to be working with these equations. At some point, these equations do have to be in your head. Okay, and I have ways to help you out with that. Basically, you're going to write the equations every time you start a problem. Okay. Now, the tactics that we're going to do, as we're going to be reading problems, we're going to try to create. This is a very quick the procedure. I have a more in-depth procedure that we'll go over. So what we're going to do is when you're reading the problem, we're going to try to draw a motion diagram and indicate the velocity vectors and acceleration vectors if you can. Okay, sometimes it's very difficult to sketch that. And you have to be liberal with how you represent the motion. You have to be able to just represent the accelerated motion just like we did in the motion diagrams earlier. We're going to that motion diagrams is going to have a coordinate system. To the right is positive, to the left is negative, up is positive, down is negative. We're going to define all of our variables that we're going to be using and list what we know. And we're going to be using the units to help us list those. Then we're going to identify the unknown, what we need to find. And then finally, we're going to use variables, this is not on here. We're going to use the variable that we don't have to actually tell us which one of the four equations to use. Okay? And so let's talk about the actual procedure. Okay? And I'm going to walk you through this one step at a time. So, my specific procedure that I use for all kinematics problems, every single one of them, it's the same, whether they're rotational or linear. This one, right now, we're going to just talk about linear stuff. We'll add on the rotation stuff later on when we get towards the end of class. Now, first thing you're going to do to help you memorize those four motion equations is write them down. And then you're going to write the variables delta x, delta t, vi, vf, and a. So write those down immediately as soon as you identify the problem as being a motion problem. Okay? Then what I do, so you're going to quickly read the problem. Then what I do is I read the problem more thoroughly and I try to make a motion diagram to kind of help me visualize the problem. Okay, some of those motion diagrams can be complicated because an object could be moving to the right, slowing down, and then it turns around and starts speeding up to the left, or it does a lot of different things. So we'll talk about that. If the motion does changes, meaning it's moving to the right and slowing down, and then it changes direction and starts to speed up and goes to the left, you might have to do this procedure twice, which means you're going to have to list a second group of variables, of 5 variables to help you solve for the second part of motion. So likely if the motion changes, where the acceleration vector is specifically changing, you're going to have to do a list of variables for the one type of motion and then a list of variables for the other type of motion. Okay? So you're going to put a question mark next to what you're being asked to solve. Okay? This is what your unknown is. Okay? Then what we're going to do is whatever numbers that we have, we're going to look at their units, and those are going to tell us whether they're distance, which would be meters, time would be in seconds, velocities would both be in meters over seconds, and acceleration is typically written as meters per second squared. From reading it and our motion diagrams, we have to decide if the direction of the velocity and the vectors, specifically the vectors like displacement, initial velocity, final velocity, and acceleration, are positive and negative. And we would type that by kind of our motion diagram showing speeding up. If it's speeding up, moving to the right, the velocities will be to the right, will be positive, the displacement will be positive, and the acceleration will be positive. So everything that we learned before, that's going to help us with this part. We're going to note the one variable that we do not have at the moment, right? So you're going to have the thing that you're trying to solve for, but typically they're going to give you three numbers. You have 5 variables. You'll be given 3 numbers. So just looking at this, you're given 3 numbers. You'll be solving for acceleration, but you also don't have final velocity. So if we have to find acceleration, but we don't have final velocity, we're going to cross out final velocity because, weirdly enough, that is the most important. That is one of the most important variables, as it tells us which equations to not use. Okay. Finally, finally, we're going to perform our algebra on the equation that we're going to use, that we've identified that we're going to use. And then we're going to solve for whatever we're asking for. Now, if you have to do, again, if the motion changes, you will likely have to carry over some of your variables from one side to the other. So if you're moving up, if you're moving to the right and speeding up, and that means you get to some final velocity, but then you start slowing down from that, then the second group of equations, this final velocity will be your new initial velocity in the second group of variables that you have to solve for. Okay? So you'll probably have to perform this procedure twice if the motion does change. Okay? We're going to go through this, so don't try to memorize this. It's something that you're going to work through and follow, but eventually at some point it'll get ingrained in you, and you could then start modifying this procedure for you. But this procedure that I've created works every time for all motion problems. Okay, so I like one way of doing everything. A catch-all procedure for everything. Okay, so this is procedural knowledge. Okay, now what we're going to do is try it out. Okay, so assuming, it's not hard to think that that in this chapter we're going to be doing motion problems. But sometimes, like on a final exam, you won't know what procedure to follow. You do kind of have to quickly read over the question and evaluate whether or not this is going to be a motion equation or a force equation or energy or momentum or torque or whatever. So you might have to quickly read this over. So, but since we know we're working on motion problems, the first thing you're going to do is write out each one of these equations. Okay? And you're going to list a set of variables, right? Delta x, delta t, v, I, v, f, and a. Write those out every time. Now what we're going to do is we're going to read the problem, okay? And we're going to try to imagine what the motion is doing. Okay? So you're driving to the grocery store at 20 meters per second when a traffic light turns red and you instantly begin to brake to a stop over 110 meters. And it says, assume your car brakes apply a constant acceleration. The question it's actually asking for two things. How long does it take for you to stop after the light turns red? What is your acceleration? So we're going to just do the first part first. So if you don't know which direction it's moving, and oftentimes problems don't give you a direction, just make it move to the right. And if you don't know what your starting position is, I don't know, choose one. So I'm going to make it start at 0 meters. So this is 0 seconds, and it's already got that initial velocity of positive 20 meters per second, right? You're traveling at 20 meters per second. And you instantly begin to brake over stop over 110 meters. That means somewhere over here, let's try to do 10, 20. Okay, so let's go by. We don't even have to use these tick marks, but I'll call this 5, 10. So 5, so 1, 2, 3, 4, 5, and this is 6. So we'll call this 110 meter. So yeah, let's call that, so 5, 10, 15, 20. So that's 1, 2, 3, 4, 5, 6. So this is 110 meters. It doesn't have to be perfect, but you know this is 110 meters to the right. Okay, and the object is starting here at 0 seconds. Now, if it's slowing down, which this object will be moving to the right and then slowing down, we know from our motion diagrams it's going to look something like this. It's going to get smaller and smaller and smaller and smaller over time until it comes to a stop right there. And that happens at some final time. Okay? Now we know that whatever these times are, if this is like 1, 2, 3, 4, I don't know how long it's going to go, and that's the final time. We know that acceleration vector is subtracting from these ones every time. So we know the acceleration is working against our positive velocity vectors, right? So we had an initial velocity that was positive 20 meters per second, and then those acceleration vectors are subtracting from it over t final parts of amount of time until finally those should be the same size, until finally it comes to a stop. So you don't have to do this every time, and obviously I went a little far into it, but here we go. When we're looking at our the stem of the problem, this does kind of help us really understand. So now I'm going to look at this and go, okay, this is showing something moving to the right and slowing down. So I'm driving to the grocery store at 20 meters per second, and I'm going to instantly brake to a stop such that my velocity final is equal to 0. And that happens at 110 meters. Well, that helps us put numbers into these variables. Okay? So we know from this we have 20 meters per second. That was our initial velocity. And we know our final velocity from our little motion diagram is 0. Comes to a stop. We know time is what we're solving for. That's our very first question that we're asked to figure out. How long does it take? So that's time. And we know it's going to get to a position 110 meters to the right of where it started. Again, if you don't know the direction it's moving, or they don't indicate it, just give it a direction I typically use to the right. And right now, we don't know acceleration, but what we do know is that it's going to be negative. So we don't know acceleration at this moment. So we have our equations. Now we need to solve for time, but we don't have the acceleration. So we don't have acceleration. So that tells us which equation to use. So looking at these 4 equations, which equation has our numbers x, vi, vf, and also the question mark, but it does not have a. So which equation does not have a in it? Right here, this guy. So that's how we chose this equation. That's how we know what to work with. This equation does not have a in it. We do know that a is going to be negative. So what we're going to do now is we're going to solve for time using this equation. So we're going to perform our algebra on this equation. Okay, it makes it easier. I know you like putting in numbers first, but rather than writing positive 110 meters every time, I can just write delta x. Instead of writing positive 20 meters per second every time, just VI, right? So that's what, and our V final, which is 0, delta t. So this is, I'm just going to go ahead and simplify this a little bit. Our VI is here, delta t. Now we're solving for delta t, so that means we're going to have to multiply both sides by 2 and divide both sides by VI. So multiplying both sides by 2, we have 2 times a half, which is 1, and then delta x we're going to multiply by 2. And then we're going to divide both sides, or I like to multiply both sides by 1 over VI. So 1 over VI multiplied by here is just 1, and so we get 2 delta x divided by VI is equal to delta t. Okay? Now let's put in our numbers. So 2 times positive 110 meters divided by a positive 20 meters per second, delta t. So this is going to be 2 divided by 20, which is 1 over 10. 110 divided by 10 is going to be 11. So this is 11 seconds. Okay? Well, I think they were asking to solve for something else, and they want to know what the acceleration is. Well, now we know everything. So now we're going to put that into our list of what we do know. And now we need to find acceleration, which should work out to be negative. Now, you could use any of these equations that has a in it. Since we have 4 variables, we just need to find a. Which one of these equations looks like, which has a in it, looks like it's the most easiest one to use? That's right, this one. V final plus a delta t. V final equals a delta t plus v initial. And then we're going to solve for a. So that means we need to, this side is actually going to be 0. So the v final is actually 0. And we need to subtract v initial from both sides, which we just get v initial on this side, which is now negative. And then we divide both sides by delta t, or multiply 1 over t from both sides, which you get negative vi over delta t. And that's our acceleration. So you have a negative, and this was a positive 20, so 20 meters per second, and our time is 11 seconds. So the seconds are gonna build on each other. So we're gonna have a, that negative is in front, and I don't know what 20 divided by 11 is. It's probably a million. 1.82. I was off just a little bit. So this is going to be 1.82 meters per second squared. Seconds squared. Okay? So this is the procedure I use every time. Okay? So let's run through the procedure. The first thing we did is we wrote down, we identified the problem, we kind of looked it over, oh, it's probably motion, because we're in the motion chapter. So we wrote these 4 equations and wrote these 5 variables. Then what we did is read the question, and we looked for the units that told us that that was a velocity. And when we were reading it, it said, you're driving to the grocery store. So that tells me that you're currently driving at 20 meters per second, which is our initial velocity. And then when the light turns red, you begin to slam on the brakes and come to a stop over 110 meters. So we didn't know which direction we were moving. We said we're starting to the right. 110 meters is over here to the right. Started at 0 seconds with our initial velocity. So we were moving to the right and slowing down. Okay. So we filled in positive 110 meters, positive 20 meters per second for our initial velocity. And we had a slow to a stop that tells us the final velocity is 0. And our question mark was, what is time? We didn't have A, so we identified which equation does not have A in it, which was this third one. We performed our algebra on it, solved for time, filled in time right here, and now we're asked to solve for the acceleration. Since we have all the variables except for A, we use the most simple equation to use and solve for that. Okay? This is one of those things that if you could follow a procedure, and you don't have to do motion diagrams, but it does help you visualize the problem. So this procedure works every single time. Okay? So again, we're in the kinematics chapter, so let's try this again, and we're going to go overtly into the procedure. So we're in the kinematics, we're going to use kinematics procedure. Write the 4 equations. Write the 5 variables. Okay? So after we do that, now let's go up and reread the problem and figure out what the problem is trying to ask us. So it says here, a sprinter is running a race. Assume the sprinter speeds up from rest until reaching a top speed of 20 meters per second at the finish line. The sprinter reaches her top speed in 10 seconds. What will be your acceleration and what will be your displacement? So let's figure out the acceleration first. Let's start with the question. We need to figure out what the acceleration is. Okay? Now, assume the sprinter is speeding up from rest. So this tells me that we have an initial velocity of 0 meters per second. And that she's going to reach her top speed of 20 meters per second by the finish line. I don't know what, the problem doesn't indicate a direction, so I'm going to make her moving to the right. And the sprinter reaches her top speed in 10 seconds. So seconds is time. I'm going to put that here. So let's do a motion diagram to kind of help us out. Starting here at 0 meters. I'm going to just put the start time as 0 seconds because it doesn't tell me anything otherwise. And later on, over here, some distance away, at the 10-second mark, she has sped up. So this is her final position. She is sped up to her velocity being positive 20 meters per second. Okay, so speeding up looks like, and I should have put that vector, I need to put that dot a little bit higher. So speeding up looks like the little dots are getting further and further apart, right? So if you start out running this speed in 1 second, and then later on are running this distance in 1 second, then that means that you are speeding up, right? You're running a further distance over the period of time. So these dots, and I think I made these things, I didn't give myself enough room, but they're getting longer and longer until finally 10 seconds later, they're really long. In order for you to speed up, that acceleration vector has to add to your initial velocity vector, which, by the way, initial velocity is 0. So starting from 0, your acceleration vector is going to be this long. This size vector plus 0 is this vector, which is your new velocity vector at v1 at 1 second, right? And then add the acceleration vector to this again, and now you have v2. I know the scale is not great on this. So 1 second, and this is going to be v1, and this is v2, and then that acceleration vector adds to v2 again, and creates your new, your third velocity vector, and so on, all the way 10 times until you finally get an acceleration. You finally get this velocity vector, which is your final velocity vector. And that occurs at 10 seconds. So it really does help. This diagram helps match up with what the problem is asking. Okay? Now, since they're moving to the right, we know their displacement has to be positive. Okay? Because if it's a positive 20, you start from 0 and you end up moving to positive 20, you're moving to the right the entire time, especially since we know that acceleration vector is going to also be positive because you're speeding up. So we know this question mark, which is our first question mark, is going to be a positive number. But we don't have delta x right now. We're going to find that out later. But which one of these equations, so let's figure out which equation to use to find acceleration first. Well, since we don't have delta x at this moment, we can't use this equation, we can't use this equation, and we can't use this equation. So we have to use this equation. All right? So starting with that equation, and I think we said our initial velocity is 0, so I'm going to just put in a 0 real quick, try to make life easier for myself. And then divide both sides, or rather multiply both sides by 1 over delta t. And we get v final over delta t is equal to the acceleration. And our final velocity is positive 20 meters per second. Excuse me, that we're going to divide by 10 seconds. So 20 divided by 10 is 2. So that acceleration is going to be a positive 2 meters per second squared. So now we know what this acceleration is. And yes, it is a positive number, so we predicted correctly. Now, let's figure out displacement, because that's what it's asking. So now we're going to move our question mark to here. Okay? We're going to remove all of our crosses. So which equation would you use that has delta x in it? And the only requirement is it has delta x, since we have the other 4 variables, the numbers for those variables. So which equation looks like the easiest to use and least complicated? Well, this one has a t squared in it. I don't like that. This one has a delta x in it over here, so I'm going to have to do a bunch of algebra. I like this equation because it looks really simple. And even one of those numbers, the initial velocity, is going to be equal to 0. Vi plus Vf delta t. And then we can just start plopping in numbers. Delta x is going to be equal to 1/2 0 meters per second plus 20 meters per second times 10 10 seconds. All right. So this is 20 divided by 2 is 10. 20 plus 0 is 20. 20 divided by 2 is 10. 10 times 10 is 100. So that positive 10 meters per second times 10 seconds is going to be positive 100 meters. And that is both of our answers. Okay, so the trick again is, let's go through the procedure again. We're doing kinematics problems, so write the 4 equations we're going to use and write the 5 variables that we're going to need to figure out. Read the problem carefully. Okay, so reading the problem, I'm trying to picture what is happening. And the problem overtly states they're speeding up from rest. And it doesn't tell you which direction, so I'm making them go to the right and they're speeding up. And I basically made a motion diagram of an object speeding up while moving to the right. And remember how we practice identifying positive velocity and a positive acceleration vector is speeding up? Well, I basically wrote that out right here. Okay, so we identified speeding up from rest. That means her initial velocity is 0. Her final velocity is 20 meters per second, and then her period of time is 10. That's delta t, and we wrote those in there. We put a question mark next to her acceleration is what we were asking to solve for first. We didn't have delta x, which told us which equation to use, which we had to use this second equation. We performed our algebra on that second equation to solve for acceleration, plugged in our numbers and found acceleration, and then filled that in here. Then we moved the question mark to displacement because that was the next question. And since we have all of those numbers, we could have used any equation that has delta x in it. And I used the simple one. I want my life to be easy. And that's what we solve for. Okay? That is the procedure. Okay, let's continue moving on, practicing the procedure. Okay? All right. So this is one that's a little bit more complicated. These other two, this was just slowing down while moving to the right. This was just speeding up while moving to the right. This is something that changes direction, but it has one acceleration vector. Typically, if something is moving to the right and then moving to the left, but has one acceleration vector, since its acceleration vector is the same the whole time, where you'd only have to do this one procedure. But on this next problem, it has 2 different acceleration vectors. So, but you could do this problem in 2 chunks and just using the same acceleration vector. Anyways, you'll see what I mean by identifying it only has one acceleration vector. Okay. So again, start the procedure by writing the equations, the 4 equations, and the 5 variables for now. Now let's read the problem and try to picture what's going on. So we're also going to identify the variables here. We have a velocity right here. I'm not sure which one that is. We have a time here, so we have a delta t, and it looks like we have another velocity right here. Okay, let's read the, and we're asked to find displacement. So we're finding delta x first. Okay, let's read the problem more carefully. A ball is moving to the right at a ball is moving to the left at 4 meters per second. So this is got to be the initial velocity. Okay, I'm going to continue reading. After 10 seconds, the ball is moving to the right at 2 meters per second. So this is definitely the final velocity. and assuming the ball has a constant acceleration. So it only has one acceleration working on it. Okay, so let's put those numbers into here. So the initial velocity is -4 meters per second. And then later on, the final velocity is +2 meters per second. We're finding displacement, and we have 10 seconds. Okay, so it looks like we don't have the acceleration just yet. But let's do something. Let's try to see if we could picture this. It's going to be moving to the left. So I'm going to put it right here. I don't know where to start this, but let's try it out. So it starts off with a -4 meters per second, and then later on is moving to the right at +2 meters per second. So the velocity vector is going to change. In other words, in order for it to go from moving to the left to moving to the right, at some point it had to come to a stop. So it's slowing down as it's moving to the left. And then finally it comes to a stop at some point in time. I don't know. And then later on it begins, now it's not moving, and it starts to speed up moving to the right until finally it reaches +2 meters per second as the final velocity. The initial velocity was -4 meters per second. So not only did it have to come to a stop in reverse directions, it's now moving. It's now moving to the right. So, and we don't know its exact position because they don't ask that. They do want to know the overall displacement from beginning to end. And in order for this negative velocity vector to turn to a positive velocity vector, there had to be an acceleration. So if you're moving to the left and slowing down, there has to be a positive acceleration slowing you down. And if this constant positive acceleration keeps pushing you, eventually you're going to come to a stop. And once you're at a stop, if it keeps pushing you, it's going to keep pushing you to the right until you start speeding up while moving to the right. So we know this acceleration has to be positive. We don't know the displacement. We don't know we don't know the position, we don't know the displacement right now, but we have to find that out. So again, we don't have acceleration. So that tells us which equation which equations we can't use. This has acceleration in it, this has acceleration in it, and this has acceleration in it. We have to use this one. So let's perform our algebra on this. 1/2 v initial plus v final delta t. Really can't perform any algebra and because it's already set up for us. So this one is an easy algebra problem. We're just putting in numbers. Our initial velocity is -4 meters per second. Our final velocity is +2 meters per second. And our delta t is 10 seconds. Okay, so delta x is going to be equal to 1/2. This is going to be -2 meters per second difference times 10 seconds. So delta x is going to be equal to -2 over 2 is -1. -1 times 10, -10. Nice. That is pretty easy. So once we have that, we're going to put in -10. And now we're going to find the acceleration. That acceleration better work out to be a positive number. Now we could use any equation that has a in it. Which one of these equations looks like it's easiest to use? Well, this has a t squared in it, and this has an a over here, so we're going to have to perform more algebra with these v squareds. I like this equation. It seems nice and simple. V final equals A delta t plus V initial. We're going to subtract V from both sides. VI from both sides. So that means we're going to get V final minus V initial equals A delta t. And now we're going to solve for A. V final minus V initial divided by delta t is going to be equal to A. And so V final minus V initial, so V final is positive 2 meters per second minus negative 4 meters per second divided by 10 seconds. So this is going to be, is that positive 6 meters per second over 10 seconds. So that acceleration is 6 divided by 10, that is 0.6 meters per second squared. Okay. So this is how to handle a problem that changes direction but has a constant acceleration vector, meaning that acceleration vector is pointing in one direction the entire time. Let's find out what to do when we have an object changing motion where the acceleration vector also changes. Okay? So again, start off by writing these 4 equations out. That will help you memorize them. And then start out by just writing the one equation set of variables right there. So write out your 4 equations again and write out your 5 variables. Now, at this point, you haven't even read the problem. You don't know you're going to have to do this a second time. Now, when you read the problem, you're like, okay, let's read it. A go-kart starts from rest. Ooh, that's just going to quickly write that VI is equal to 0. And it's going to be speeding up, moving to the right with an acceleration, so to the right, of 2.6. So we know that is a positive acceleration. So that's our acceleration for the first part here, over a distance of 120 meters. So we know that displacement is, and since it's moving to the right, is positive 120 meters. Okay. Something happens, and it begins to slow down with a different acceleration of 1.5 meters per second squared. Okay, until it has a final velocity of 12 meters per second. And then they want to know what is the total displacement of the cart. Okay, this is all over the place. I'm not sure what to do. Let's just start. Let's start here, and if I don't know where to start, let's just start here at 0 seconds with the initial velocity of 0, right? It's not moving, 0. Now, we know it's going to be accelerating to the right, so it's speeding up as it's moving to the right, so that acceleration is positive 2.6, and that's going to be adding to it over a period of time, right? And then it's going to be getting bigger as that acceleration adds to it every time at positive A. And then something happens right here. And then he begins to slow down. So at this point, this is 120 meters. I'm trying to picture what's going on. And so at this point, it's got a positive acceleration, but at whatever time this is, something happens. And the acceleration vector turns into a different direction. It's now not this. This is positive 2.6 meters per second squared. Now it's pointing the opposite direction because the object's still moving to the right here, but now it is pointing to the left. Whatever acceleration is here, which is negative 1.5 meters per second squared. Now that acceleration vector is getting smaller. So it's now going this size. So at this point, that is whatever the final velocity is for the first part. And now that acceleration is going to be subtracting from this and making it smaller until we reach a final velocity of 12 meters per second, still moving to the right. And they want the total displacement all the way to right here. Okay, well, since the acceleration vector is changing direction, we're going to need to do this twice. Okay, so let's solve for the first part first. Okay, and let's solve for every variable that we have. Okay, so we know that it starts out with a velocity of 0, and that the next number we know it's got a positive acceleration of 2.6 meters per second squared. Okay, and it covers that that acceleration is working on it for a total distance of 120 meters. Now we know this is going to get to some final displacement, and we just call that x final, which is this huge distance past 120. Okay, we don't know the period of time, we don't know the initial velocity here, but we do know the final velocity is going to be positive 12 meters per second to the right, and that acceleration, which is going to be negative because it's slowing it down, is negative 0.5 meters per second. Now, I can tell you this. We have three numbers. We can figure out delta t and vi, which is typically what I do whenever I do these problems. I just solve for all the variables. But I wanted to think about it. See this v final here? That's the final velocity here, right? But that's going to be the initial velocity going into the second part of the problem. Okay, so just real quick, let's figure out everything. Let's figure out all this stuff, delta t and v final. Let's figure out final velocity. Let me see. So you want to do, let's figure out the final velocity first. Okay, which means we don't have delta t. Okay, well, to figure out the final velocity, we can't use delta t for this part, so we don't have we have delta t there, there, and there, so we have to use this last problem. So v final squared equals v initial squared plus 2a delta x. And to find that final velocity, we're going to have to square root both sides. V initial squared plus 2a delta x. Now let's plug in our numbers. Our initial velocity is 0, so that's pretty easy. 0 meters per second that we're going to square, plus 2 times a positive 2.6 meters per second squared times a positive 120 meters. Incidentally, if you get a negative number in here, you made a mistake, right? Go back, if you do get a negative number inside the square root, which is an imaginary number, go back and try to figure out your vectors are off somewhere in this part. So this is going to be the square root of, let's do some calculator business. It's going to be 2 times 2.6 times 120, 624. So this is 624 meters squared per second squared. I'm double checking my units. Once we square root that, that'll become a meters per second. So this is a positive number in here. Now when we square root things, you actually remove the direction of that vector. But this is meters per second. So we'll have to add that direction after we're done with this. So square root of 624. 624 square root 24. So let's just round up to 25. Make it easy. So we know this is going to be 25 meters per second. All right. Now we know it's moving to the right the entire time. So we know this is positive 25 meters per second. Since we're here, let's figure out the time. We don't know, we might need it, I don't know, but let's just figure out the time. Now, since we have everything here except for time, we're just going to use our easy equation again. As long as it has time in it, since we have the other 4 variables, we're just going to go ahead and jump to that to figure out time. We've done it over here. We just take v final minus v initial over a, which is equal to delta t. So we use that second equation, and we're going to put in our numbers. Our final velocity for this first part is positive 25 meters per second. Our initial velocity is 0 meters per second, and that acceleration is going to be positive 2.6 meters per second. Incidentally, if you get a negative number for time, again, you've made some kind of sign error. So double check that. So 25 divided by 2.6, that is 9.62. So 9.62 seconds, which I'm going to write in here. Now, like I said, now for the second part, at 120 meters, we know he's traveling at positive 25 meters per second. That is the new starting velocity, that he's going to be slowing down from that velocity to 12 meters per second with this acceleration. Okay. Now, let's figure out the displacement of this. Okay. Let's solve for this displacement, and then we'll also solve for the time. Put our question mark here. We don't have delta t. Okay. So we don't have delta t. Well, this equation has delta t in it. This one has delta t in it. This one has delta t in it. So we are using the same equation again. We're just solving for something different. Plus 2a delta x. We're going to subtract both sides by v initial squared. I'm going to subtract that from both sides. And then we're going to get v final squared minus v initial squared equals 2a delta x. We're solving for delta x, so we need to divide both sides by 2a. Or rather, I'm going to multiply both sides by 1 over 2a, which is going to give me this over 2a. delta x. Let's put in our numbers. So we got a positive 25 meters that we're squaring, and we got 12 meters per second that we are squaring, and we're going to divide that by 2 times a negative 1.5. What is that? Negative 1.5 meters per second squared. Okay, so this delta x I forgot that is supposed to be a negative number right here. And you know what? I kind of made a mistake with that. It's slowing down to 12. So that's the final velocity. I made a mistake. I'm glad I realized it. So the new initial velocity is 25 meters per second, and it's slowing down to positive 12. So positive 25 minus, so there we go. So let's figure this out. 2 times 1.5 is 3, so 12 minus 25 equals, and we're going to divide that by a negative 3. Equals 4.33. So the displacement is a positive 4.33 meters per, just meters. Okay, so now we know the displacement. And technically we're done with the problem. We just add 4.33 to 120 and we're done. But I like to be thorough, and now let's figure out this. Time. Well, since we have all these numbers, again, we're just going to use this equation, v final minus v initial. You're going to do this a lot. You're just going to know that that second equation right here is going to either be v final minus v initial over a, or v final minus v initial over delta t, depending on what you're being asked for. So our final velocity is positive 12 meters per second. Our initial velocity is a positive 25 meters per second that we're subtracting from it, over negative 1.5 meters per second squared. Looks a lot like this. It is drastically different. The squares and the 2 changes a lot of things. And it changes it such that we're solving for delta x to solving it for delta t. So, and if you want to know how we did that in the last video where we derived how this is v final minus v final squared equals v initial squared plus 2a delta x. Okay, so that's going to be 12 minus 25. We're going to divide that by 1.5. That's going to be negative, and equals. So that's going to be 8.67 seconds. So we know all of these things. So we know the total time. So the total time from beginning to end is going to be 9.62 seconds plus 8.67 seconds. That's the total trip. Which is 18.29. So this is from beginning to end. And we know the total displacement from beginning to end, which is delta x, which was given the 120 for the first part, plus 4.33 meters for the second part. So from beginning to end, it's going to be 124. Well, something happened on my whiteboard and it just disappeared. But the final answer for that was positive 120 meters plus 4.33 meters. So the total displacement from beginning to end over that 18 plus seconds is 124.33 meters positive to the right. Well, I hope you learned a lot, and we are moving to the last section of this module, which is 1.10 for the college physics students. If you're in university physics students, there is one more part, but we will go through that, and that'll be some calculus. All right, have a good day.